So we'll go ahead and write the problem out. And the problem pretty much has three members, and I believe they're wood members actually. And so what's given is that the shear load V is equal to 250 pounds. And there are two nails that are coming in on one end, two coming on here, right? And the way I kind of explain this, right, is it's very similar to like if you were to go in and out, you have your cheeseburger, right? And if you were to, if you didn't have the wrapper and you were to kind of bite into it, right, you know, there's a chance that this middle part will kind of go out and then you'll get all dirty. And one of the solutions is that you don't have it in and out, but it would be to kind of stick something through like a club sandwich to kind of keep all that together, right? So when you have these members and you wanted to connect it so that they move together, what you end up doing is that your moment inertia actually increases. Okay, so the advantage of it is this. Besides the fact that we're trying to solve for it, and besides the fact that we want to just move on with our lives and solve the question, the thing is, it's like, well, why the hell do we have to nail it? Why don't we just slip it together? I don't care if it slips. Okay, and the reason is this. It becomes a moment inertia discussion. So let's say, and we'll solve real life or real questions. This is 3.5 inches. This is 1.5 inches. And this dimension kind of repeats, right? 1.5, 1.5, 3.5, and all that stuff. Okay. So we'll calculate moment inertia as three separate pieces and in one solid piece. Okay. And you'll see why we want to stitch it together. And then we'll start solving the problem. So I'm going to teach you why we need to be doing it. Okay. And what the value is. Okay. So we'll say that this is together. And this is stitched. Oh, no, sorry. Oh, no. Hold on, guys. Let's see. Hold on a second, guys. Okay. Sorry, my battery's running low. So this is if the members were stitched together looking at this whole, and then this was a three separate pieces. Okay. And so the difference is that here you would look at it as a solid piece. Five times 3. So that's 4.5 inches. Can somebody say like hi or something so I know that I'm not talking to myself and people are still here?
Yeah, you're good.
Okay, great. Okay. And this is 3.5. Okay. So the other part is going to be three separate pieces, right? We have three times of this. Ooh, technical difficulties. Okay. And so the question is, okay, well, let's solve for it, right? So this is equal to, I is equal to 112, BH cubed, base is 3.5, H is 4.5 to the third power. Okay, and can somebody solve this for me while I'm setting the next one up? The other one is I is equal to, we have 3 of them times . 112, base is 3.5, the height is 1.5 to the third power, and because we have 3 of them, right, because we're stacking 3 together, but they're not stitched together, so you actually account it separately, we're getting 26.58. And then I need the answer for this one. Looks like it's like 1 or
I got
less than that.
2.9.
2.95.
Yeah.
All right. So what happened here? We have the same area between left and the right side. Okay. The difference is that on the right side, we didn't take advantage of parallel axis theorem, because if we were to include plus AD squared of the parallel axis theorem, these two numbers would actually become the same. And you know what? Let's do it. Okay. So the AD squared, if we have 3, right? We essentially, the middle one, the area is there, but the D is actually 0, so we can ignore that. So here, then we're going to have this D and also this D, which is symmetric, right? So we could just do 2 times AD squared. Y'all agree? I'm going to assume yes. Okay,
Yeah.
so what does that mean?
Yeah.
That means we're going to plus 2, and the area is going to be 1.5 times 3.5. And D squared would be 1.5. Is that what it would be? I think so, right? Yes.
Yeah, I think so.
1.5 squared. Okay, so what is this equal to?
It's the same.
It does equate to be 26.58, correct?
Yeah.
Voila. So what I'm trying to say is the whole point of putting those toothpick together to connect the two is to get this value to come out. Sorry, that's 26.58 minus the 2.95, right? Because that's what's in there. And so this one would essentially be 23 point something, right? So do you guys see what we just did now?
Yeah, I think I follow it. So you take, what is that? The D is just a neutral axis between the two?
Yeah, yeah. And so by stitching it all together, right, you kind of, you take advantage of physics, the moment inertia, specifically parallel axis theorem, to get a higher moment inertia. And when it comes to structures, having a higher moment inertia is for the most part what you want. Okay. So, but guys, just by putting those toothpick in there, right? The question is, how much stronger is my member? How, because that actually later on equates to how stiff a member is. So if we did this, what is the advantage?
Nine.
9 point something, right?
Yeah, 9.01.
Yeah, so think about it this way, right? If you worked at In-N-Out and someone said, okay, the In-N-Out burger costs $4, right? But if you put a toothpick in it, right, you can sell it for $36. Would you do it?
Easily.
Right? That's essentially what we're talking about here, right? Just by adding those toothpicks, boom, you get 9 times more, just like that. And that's why we want to know what the shear flow stresses are, right? What that toothpick, the shear force that it's feeling, right? Hold on, let me get some video on. Sorry, I lost you guys. So, okay. I'm just trying to figure out how. Okay, so if you guys can see my screen, like the toothpick will feel this kind of shearing force, right? And that's in the kind of the same direction as you bite on a burger, the inside portion kind of comes out, right? And so that's why we want to do it. Okay. Now the question is either going to be, is that toothpick strong enough, or what is that? What kind of shear force is that toothpick going to feel? Right. It's either one of the two questions. Okay. So in this question, it's asking what kind of shear force does this toothpick feel? Okay. So now now that we understand why we want to do it, let's try to solve the problem, right? So do I have to draw it again? Let's see. Let me try to steal it like that. Ooh, shoot. Ooh. All right. And so the question says that the nails are spaced at 2.5 inches. And what that means is that if we were to extrude this out, okay, that toothpick, imagine this is like a club sandwich now, right? Not a club sandwich, like a Jersey Mike's. I don't like Subway, guys. I'll put it on the record. Subway sucks. Subway's not amazing, guys. Guys, Subway for their $5, all they're giving you is one slice of meat and a whole bunch of carbs. And that's why it's cheaper.
Subway is overrated.
You know, Subway was really good like about 20 years ago. Yeah. So anyways, my drawing sucks, but you guys get the idea, right? And then the stitching would also occur below, right, at every 2-inch spacing. You guys follow?
Yeah.
Okay. And the point is to stitch this, right, to the center one. And because it's symmetric, top to bottom, it's mirrored from the neutral axis, right? So here's your neutral axis. And it's mirrored, right? Because it's mirrored, essentially, if you solve for the top one, you solve for the bottom one also. Okay. So so in my mind, the question is it shear flow or shear stress? Okay. So shear flow, let me do blue. VQ over I. And stress just literally means that there would have been a T right here, okay? But we're not doing that. We're just doing shear flow, okay? So shear flow is saying, well, what's a V? Well, it's right there. Boom, done. I. Oh, shoot. So the I is going to refer to the total moment of inertia. And actually, we could take advantage of what we just did up there. It's 26.58. Wow. And I didn't even plan for that, guys. Now, the question is, well, is the moment of inertia of that one item, two items, or the entire thing? It's a whole shebang, guys. So I refers to the entire thing. Okay. Q refers to the item that you're looking at. The stuff that's in like pink or light red, okay? So that's the Q that we're going to be focusing on. And Q, you may not remember, but it was actually gone over or explained to you in statics as the first moment, okay? Like the first order, right? So then this is equal to right? So can somebody tell me what the area of the pink is? Well, it's going to be a rectangle, so it's going to be 3.5 times 1.5. So what does that come out to be, guys? 5.25. Good. And the distance, it's going to be pretty obvious, but check it out. It's the distance from the neutral axis to the center of where you are focused on, the member that you are focused on. And therefore, that distance is 1.5. Very good. See, isn't this problem a lot easier when I solve it?
Definitely.
Yes, sir.
1.5 inches. All right. Just plug and chug, guys. Boom, boom, boom. So what does that equal to?
It's 74.07.
Yeah, I got the same.
74 what?
Inches.
Just okay, 74. It's pounds per inch. Okay, somebody says 74.07. Okay, so if you guys are headed to aerospace, the answer is 74.07. If you guys are doing structural engineering, 74 pounds will do. Okay. Anyways, it's really not going to change your answer too much. It's fine. Okay. Now, what does this mean? Right? What does this mean? What that means is that in between, right, you essentially have this shearing force that in total is 74, this total resultant is 74 pounds for every inch, meaning that for 1 inch, you have 74 pounds of shearing force. Okay, shear, right? Shearing force. And then if you were to go to this 1 inch past, then you have another 74 inch. Okay, so one way to look at it is that if you were to say buy glue and they had some property saying that the shear stress is capable of saying having a 80-pound per capacity per whatever width that we have, then that means that you could put that glue on and everything would work. Okay, so that's one thing. So with that idea, hopefully that kind of makes sense now. Remember, that's 74 per inch. The next inch would have another 74. The following inch would have another 74. Now check it out. We know it's 74, right? And we have how many nails? We have 2 nails. So we're going to share it. 2 nails will share the 74 pounds per inch. So 74 divided by 2 is
37.
37 per nail, right? Per inch. And what is the spacing? Well, the spacing is 2.5 inch. So shoot, if it's 2.5, I'll take 37 times 2.5 inches, right? Yeah. So that cancels out, right? And we know it's per nail. So what is 37 times 2.5?
92.5.
92.5 pounds of shear. So what does that mean? So that toothpick, right, would actually feel a shearing force of 92.5 pounds. Guys, that's pounds, not hashtags. Okay, when I first started teaching this course, there was barely, like, Instagram barely started, so I never had a problem. So it's not hashtag, guys. It's pounds. Okay, so that shears it. So if we want to take a step forward, we'd be like, well, what's the shear capacity of that nail? And we would say, well, the shear capacity of that nail is 100 pounds. Well, then does it work? Yeah, it does, right? And that's actually your answer. So final answer. Any questions? Okay. Hopefully you guys like that. It's all the other problems just pretty much something very similar. Okay, like for example, if you had like a profile that maybe had something like this, right? That's essentially going to be the same. You would take your pink highlighter and highlight what member you're going to be focused on. It's got to be pink, guys. Okay. And then you find what that distance is. Neutral axis. That's your D distance. Okay. And then again, on this problem, you have nail 2, and then whatever spacing you got, right, of the nails will determine. Or the reverse question, a question would be, hey, you know what? The nail can take 250 pounds. What's the spacing that I can get away with? So that could be another question. What is this distance? Right, that could be a question. You get what I'm saying?
Yeah.
Okay. So that concludes that portion of it.